It's all about asking the right questions. Why does the mechanism go that way? Why doesn't that intermediate lose a proton? What is this section about, really? Is there one notion to understand which makes everything else clear? Is there a challenging question that proves understanding? Question to learn. Formation of enols and enolates and then halogenation is a very good reaction. It's easily controlled. But alkylation of enolates is trickier. That's unfortunate because we would like to do this reaction to extend an alkyl chain in an organic molecule. One problem is that aldehyde enolates particularly, and to a lesser extent ketone enolates, can undergo alternative reactions. Consequently, chemists have devised some pretty clever solutions to these problems. One of the first considerations is which base to use. If the base is too nucleophilic, like butyl lithium, then it might add to the carbonyl rather than deprotonate the enolizable hydrogen. LDA can be prepared by using butyl lithium to deprotonate diisopropyl amine, which gives a less nucleophilic base. If phenylmethyl ketone were deprotonated using LDA, an enolate would be formed cleanly. Deprotonation of NN-dimethyl amides proceeds cleanly to give a Z-enolate. Alkylation of amides of this kind are very easy to control. What about the problem of a ketone with different substituents on either side? One solution is to condense with NN-dimethyl hydrazine to form Z and E hydrazones, wherein the E isomer is the most stable. If that is reacted with LDA, deprotonation occurs on the least hindered side to give an enolate in which that geometry is stabilized by coordination to lithium. Alkylation of that hydrazone enolate occurs on the same side, and then hydrolysis of the hydrazone gives back our ketone alkylated as desired. Another way to activate aldehydes and ketones to nucleophilic attack is to temporarily form silyl enol ethers. TMS ethers can be formed under thermodynamic conditions with a base such as triethylamine at room temperature. Alternatively, kinetic silyl enol ethers can be formed by deprotonating a ketone on the least hindered side, then adding trimethyl silyl chloride. This reaction occurs on the oxygen because of the strong oxygen-silicon bond strength. It's also possible to take ketone enolates and alkylate them to form methyl enol ethers. Here, a very hard electrophile, trimethyl oxonium, is used for that alkylation reaction. Silyl enol ethers are very easily reacted with electrophiles. In the simplest possible case, that could be a proton to give back the ketone, and it could be a more interesting electrophile to give a substituted ketone. Enamines are similar to enol ethers. Recall that enamines are formed from aldehydes and ketones by reaction with secondary amines. Ketones that have two different ways to enolize will form the least hindered enamine in this reaction. Alkylation will occur on the least hindered side. After that, hydrolysis of the iminium that's formed would regenerate the ketone, but with a substituent. There is nothing special about pyrrolidine in these reactions. Any secondary amine could be used. And there's nothing special about methyl iodide. Any reactive alkylating agent like benzyl bromide could be used. It's even possible to use acyl chlorides to form 1,3-dicarbonyl compounds. We have learned about deprotonation of aldehydes and ketones with LDA, silylation and alkylation of the enolates that are formed. Then we learned about using enamines to alkylate on the least hindered side of a ketone. Bye-bye.